So as an extension to our discussion of electromagnetic radiation, I would like to stop and briefly mention the Poynting vector. This is a fundamental quantity when we're talking about the propagation of electromagnetic waves, and is heavily related to the work we saw from Maxwell. Now, the Poynting vector is named after a person, Mr. Poynting or Dr. Poynting. It's not about pointing with your finger or anything like that, although the direction a wave is pointing does happen to relate to the electric and magnetic fields of that wave, which is a nice coincidence. So if we look at a wave, any electromagnetic wave, it is an oscillating E electric field and B magnetic field 90 degrees to one another. Now, the arrows here show the direction of propagation or movement of this wave. As you can see, electric and magnetic fields are 90 degrees, and you can see the directions that these are expanding and contracting in, which direction our waves are moving in, and you can see this is moving from the left to the right. If we take our E and B fields and we oscillate them in the opposite direction, we will get a wave that moves from the right to the left. So, by studying the behavior of the electric and magnetic field, we can talk about how the wave will change, how it will change over distance in terms of its intensity and the power that it will deliver. So as we discussed before, our fundamental relationship when we look at the electromagnetic spectrum is basically C equals F lambda. The speed of light is the frequency multiplied by the wavelength. Different frequencies of electromagnetic radiation, of course, will have different wavelengths. They will end up also at different media have different speeds. C is the 3 times 10 to the 8 speed of light constant that we use in a vacuum, which is very close to that through air as well. But in different media, they will behave differently. So when we talk about light, what we're really talking about is electromagnetic radiation that consists of an electric and a magnetic component, both 90 degrees to one another. And of course, as I said, they can propagate through a vacuum. Now, this basically follows the right-hand rule that you should already know. Here's the electric component, here's the magnetic component. If we put these 90 degrees to one another, we'll end up with a third component of S, the direction of our wave, the direction that our wave will move in. And it was J.H. Poynting, John Henry Poynting, who came up with this, somebody who was not far from my actual hometown. And he looked at the power that's transported by an electromagnetic wave and figured out that this was electric and magnetic fields that were changing in time. Now, if our E and B fields, our electric and magnetic components, are changing, so too is the Poynting vector itself. This means if we're looking at the intensity of a wave at any one particular time, and the wave is always changing, as we know it's essentially moving up and down in terms of its intensity, this means that our propagation direction isn't always constant, but varies from 0 to some maximum value, because everything is varying as a sine wave, both the electric and magnetic fields. So, if we really want to measure the energy of a wave, we have to look at the Poynting vector, but we have to look at it over a complete wave cycle to get the intensity of the wave in watts per square meter. So this is what we see. So what we will say is the intensity of our wave gives us S, which is our Poynting vector, which is equal to 1 over c, the speed of light, times mu0, which is the permeability of the magnetic component of the wave, times E squared, which is our strength of our electric component. If we substitute in here for the variation of that intensity, sine squared, well, the average of sine squared times kx minus omega t, we find that the average of sine squared for one complete cycle of our wave is actually a factor of a half. So I, conveniently, dumps a lot of its baggage here and gives us the intensity of the wave as 1 over 2c mu0 times E squared. This is the mean electric field, or if we're looking at it in terms of the root mean square, I will be 1 over c mu 0 RMS electric field squared. So there's our relationship. Now, in terms of the energy density, the amount of energy that's contained in both the electric and magnetic components, they should be identical. One is giving rise to the other, and they're both propagating, one interacting with another. This means if we look at the energy that our wave is going to hold, it'll have an energy UE, which will give us 1/2 epsilon 0 CB squared, or if we propagate this through, and if we think about this, this will give us 1/2 epsilon 0, here being the electrical permeability of free space instead of the magnetic here, times B squared over our permeabilities combined, which will give us 1/2, this will cancel, B squared over mu 0. This is the magnetic strength of the wave and the magnetic permeability. So here we have an expression purely in terms of the magnetic part of the wave. This means if we look at the energy of our wave, or more normally the energy density, we can look at it in terms of the electric part, and this is the important formula here, U is epsilon 0 E squared, or B squared over the magnetic permeability of mu 0. And this enables us now, if we can talk about the intensity and energy that comes from any particular wave, this means we can look at the intensity of a wave and see how much energy is actually delivered, or how much power we're getting from a particular electromagnetic wave. And this has a lot of applications, from sunlight impinging on the Earth all the way through to radio transmissions and attempting to send microwave and radio communications from one source to another. So first of all, let's take a look at this in terms of solar energy. The intensity of sunlight on the Earth is about 1000 watts per square meter, or 1 kilowatt per square meter. If we look at an 8 by 20 meter roof, we can see how much total power we could have hitting that roof. And this is why a lot of countries are now mandating solar cells on the roof of buildings, and it does help in terms of heating water and such things in the home. But of course, we're living in an area which tends to get a lot of snowfall and doesn't see the sun a lot, so there are some disadvantages there in using solar energy in some parts of the world. But if you do happen to live somewhere sunny, the intensity on your roof will be 1 kilowatt per square meter. That's our power per unit area. The power in an electrical sense here will be I times A, the intensity times the area of the roof. So this is the intensity. We're getting 1 kilowatt per square meter, so 10 to the 3 watts per square meter, and multiplying that by A, 8 by 20. This will give us 0.16 megawatts. That's 0.16 times 10 to the 6 watts. Now, in this particular case, we can see that this solar panel that we're looking at here has a 1.2 by 0.74 meter size. That means the power that this solar cell shown here will deliver is about 880 watts. Now that's really useful. That means that you're getting a lot of power, a lot of energy can be harvested from something like a solar cell. Unfortunately, the reason that solar cells will not completely replace power stations is the fact that their efficiency is only at the best at about 10%, and most sit at about 6% efficiency. That means you don't get a lot of energy from a solar cell because the efficiency of converting sunlight straight into electrical current is so very, very poor. Now, I'm not saying solar cells are a bad idea. When you're actually looking at free energy coming from the sun, you may as well harvest it, but I really don't feel that solar cells will be the solution to our energy problems. Not at this efficiency. So when we're talking about an electromagnetic wave, what we're actually talking about is a spherical wave in most cases, unless it's been designed to be shaped in a specific pattern. but the intensity of the wave, I, is the power per unit area. So if we know the power of our wave here, we can divide it by essentially a spherical distribution of 4 pi r squared, and we can get an intensity of our wave at any particular point. This is often true of a point source that's emitting electromagnetic radiation, such as a radio antenna here, which we can consider is emitting radiation from one specific source. And we've seen some of these kinds of designs from our previous slide set. Additionally, if we were to talk about the intensity of light from the sun, then saying a spherical distribution from the sun is quite a reasonable approximation, which of course sunlight, radio waves, these are all part of the same spectrum. So if we emit power from a point source and it goes out in a spherical sense and propagates outwards spherically as per this diagram, then the power emitted by the source covers an increasingly enlarged area. As the radio wave moves outwards, it'll get bigger and bigger as a factor of 1 over r squared as the wave travels outwards. So let's take a look at an example of this. Here we have a radio station antenna, and it's transmitting a 10 kilowatt signal, so 10,000 watt signal, or 10,000 joules per second, at a frequency of 100 megahertz, 100 million hertz. Find the amplitude of the electric and magnetic field strengths 1 kilometer from the antenna. So our red area here is the area 1 kilometer away. So here we are sitting at 1 kilometer, and our wave will propagate out to this distance. You may have seen from our previous slide, I was basically P over 4 pi r squared. We're provided with the power from this particular problem. So this is 10 kilowatts divided by 4 pi times a 1 kilometer squared radius. If we convert our units, what we'll end up with is 0.8 times 10 to the minus 3 watts per square meter. A couple of different m's here. One is megahertz, this m is smaller, so this is milli. This means if we want to find out the intensity of the electric part of our wave, we need to go back to the expressions from our Poynting vector. I was 1 over 2c mu 0 times the electric part of our wave. So E becomes root 2c mu 0 I, which will give us 0.775 volts per meter. Doing a similar thing, but this time utilizing our magnetic expression, we can say that B is E over c, where c here would be the speed of light. So this will give us B is E over c, which will end up giving us 2.58 times 10 to the minus 9 Tesla. Check the units here. Your electric component here for this case will come out in terms of an electric field in volts per meter, and your magnetic field, of course, in terms of the magnetic field, in terms of our SI unit of Tesla.